Welcome to today's Meow seminar with Sajin Koroth, who is currently a postdoc at Simon Fraser University, will soon be starting as an assistant professor at the University of Victoria. And Sajin is working, among other areas, in communication complexity and has been an active player in some of the exciting results in this lifting revolution that is sweeping through communication complexity and all of theoretical computer science. And he will tell us today about lifting with inner product and other low discrepancy gadgets. Please, Sajin, over to you.
Thank you, Jacob, for that wonderful introduction. Thank you, everyone, for coming. Yeah, so this result is a couple of years old, so I'd like to give like a high-level overview of general lifting theorems and sort of this meta proof technique that underlies quite a lot of these lifting theorems. And yeah, please feel free to ask questions at any point. So at the first part, I'll focus mostly on the high-level details and giving some intuitions. And then the second part, we can get into the technical details of the lifting theorems that I present you. Yeah, so let me just briefly begin by introducing what lifting theorems are. So these are theorems which transfer hardness results from very weak models of computation to strong models of computation. A typical weak model of computation is the model of query algorithms or decision trees. For example, this is a decision tree for computing the OR function. In this model, you can only access the inputs by querying it one bit by bit. So here, like you query the first bit, this is the 4-bit function. So you query the first bit. If it's 1, you already know that the output of the function is 1, then you stop. Otherwise, you query the second bit and so on and so forth. So query algorithms or decision trees are sort of the Goldilocks zone where there are enough interesting lower bounds, but for many interesting problems, we can actually prove lower bounds in a straightforward manner. It's also the model where like many interesting algorithms, especially in quantum algorithms, were discovered. Yeah. So, and the idea is to use the results from lower bounds and upper bounds from this very weak model of computation to a strong model of computation, which is communication complexity. Okay, so we in this talk we'll be focusing on two-party communication complexity, and we're assuming that like there are two players, Alice and Bob, and in two-party the inputs are divided into two parts. But in the decision tree model, there is like no partition of inputs. So what we do is like we study the complexity of a function in the decision tree model by transporting it into a different function in the communication model by composing it with what we call a gadget. So what the gadget does is that it gets its independent inputs xi and yi, and it produces, in some cases, a 1-bit output. For today's talk, it will be a 1-bit output. And these 1-bit outputs are the inputs to the function in the decision tree model. So, and in the communication problem, Alice gets x1 to xn, Bob gets y1 to yn. They both know f and g, and their goal is to compute f compose g. Okay, so let me give you some examples of very interesting lifted functions. For example, if you're interested in one of the most famous functions from communication complexity is the disjoinous function or its complement set intersection. So in set intersection, Alice is given a bit string x1 to xn, and Bob is given a bit string y1 to yn, and they want to know if there's any index I where both xi and yi are 1. So if you think of these inputs as representation of sets, that means that like I is, if xi and yi are both 1, then I belongs to the intersection of the set represented by x and the set represented by y. And this is a natural way to write this set intersection function as a lifted function. So you take f to be the OR function, and G to the AND function on 2 bits, and take AND of xi and yi and take an OR of these bits. So if there's any index where I is in the I is in the intersection, then xi would be 1 and yi would be 1, and the output of this AND gate would be 1, and so the output of the OR gate would be 1 as well. Whereas if the sets x1 to xn, the set represented by x1 to xn, and the set represented by y1 to yn do not intersect, then all of these AND gates would evaluate to 0, because at least one of x1 or y1 would be 0, and the output would be 0. So, like, yeah. So this was a simple example. So what do lifting theorems do? Lifting theorems have this general format which says that, okay, for a carefully chosen gadget G, and for any function f, the communication complexity of this lifted function f composed G is equal to is approximately equal to, there's some constant factors that I'm hiding, is equal to the decision tree complexity of f times the communication complexity of G. So basically this relates the communication so communication complexity is this hard model. It just says that for a lifted function and for an appropriate gadget, the communication complexity is directly related to the decision tree complexity. So for example, if we had a lifting theorem for the AND gadget on 2 bits, then we could prove that the communication complexity of the OR function composed with AND gadget is equal to decision tree of the OR gadget. This would immediately follow from such a lifting theorem, and this would retrieve like the classical result that disjointness or set intersection requires communication complexity almost omega n. So far I did not define the models of communication and models of decision tree. So lifting theorems are proven in various models like deterministic, randomized, etc. So in general, like the holy grail is to prove a lifting theorem in either deterministic or randomized setting where the gadget is of constant size. And the size of the gadget matters because, like, when you consider the composed function f composed G is a composition of f which is on n bits, and G which is on m, let's say it's on b bits each. So G is a two-party function, so each of the players, let's say, gets b bits. But we'll also consider asymmetric gadgets where the inputs of one player could be much larger than the input of the other player. So if this is a setup, then f composed G is a function on n times 2 b bits. So whenever we translate a function from the query model to the communication model, there is a loss in terms of the input size of the function that we get, which is controlled by the size of the gadget. So if we have if the gadget is of considerable size, then the resulting communication lower bound also degrades. But if it's constant, then this is, yeah, sorry.
Yeah, and just to have it, so what you're lifting is the decision tree complexity. I think you have it, had it on the slide, but I'm not sure if we said it, just for the record, that this is like the worst case number of questions asked, or the length, I guess the height of the decision tree. Yes.
Thank you. I forgot to mention that it was in the picture. Yeah. So basically, what you were saying is that, like, yeah, this is for sorry. So this model, the cost is the depth of the decision tree, which is sort of the worst case depth on any possible input. So for example, here in the 4-bit, like for the OR function, the worst case depth is, in the deterministic case, is n bit. So that combined with such a constant gadget lifting theorem would give us that the communication complexity is almost omega n. And because of applications of communication complexity in many other areas, lifting theorems have been able to solve many long-standing open problems in a large set of sub-areas of theoretical computer science. And more importantly, they've been very useful in proving separations, which in many models like communication complexity, quantum communication, etc. So usually you want to show that like two measures, let's say, for example, classical randomized communication complexity is different from classical, the quantum communication complexity. So what you do is like you can use an lifting theorem to lift a function where the quantum query complexity is comparatively smaller than the classical randomized query complexity, and the lifting theorem naturally takes that separation from the query world onto the communication world. Okay. So, and the lifting theorems are usually proved using this two-part recipe, and one of them is an easy direction, and one of them is hard direction. Oh, I also did not define communication complexity if I've communication complexity formally, because we will be talking about both deterministic and randomized communication complexity. In deterministic setting, the communication complexity of a function is the communication of complexity of the best protocol that computes it, and in general, it's the maximum number of messages that Alice and Bob exchange on any input to compute that function. And randomized is like defined similarly. So the easy direction of the lifting theorem, which is this one, it says that the communication, the lifting theorem says that communication complexity of this lifted function is exactly equal to the decision tree complexity of f times the communication complexity of g. So the easy direction says that this communication complexity is upper bounded by the decision tree complexity times C of g. And this is very easy to see. Suppose we have a decision tree that computes f. We can turn that into a natural protocol as follows. So let's take this example of f, which is the 4-bit OR function. And f is defined on variables z1 to c4. But now we have composed f with a two-party gadget g, which takes inputs xi and yi. Xi is with Alice and yi is with Bob. So now if we can assume that both Alice and Bob have access to this tree, and they can simulate this tree as follows. So whenever the tree queries a variable zi, Alice and Bob use the best protocol for g to solve g on xi, yi. So for example, if the tree asks for z1, we just compute g of x1, y1, and this takes communication complexity of g many bits to do. And once they know the answer, they know which path on the tree to take. So they do this simulation until they reach the leaf of the tree. So this shows that the communication complexity is the depth of this tree times the cost of computing g, which is communication complexity of g. Okay, so this is sort of the easy direction, and this easy direction goes through for many models like randomized decision tree to randomized communication, quantum decision tree to quantum communication, etc. And the hard direction says that, so the hard direction says that, like, in fact, from a communication protocol for f compose g, we can also get a decision tree computing f. So the hard direction usually follows this recipe of designing a meta decision tree. So what is this decision tree to? Its input is like z, which is the input to f, but it cannot see the input. It only has query access to z. But the extra information is that we are giving the best protocol pi that solves f compose g. So this decision tree algorithm apart from having query access to Z, also knows this protocol pi. And what it would try to do is it would try to find or to sample or find a leaf of this protocol pi, and based on this leaf, output an answer to f of Z. Okay, and we would like and to do this sampling, we will need querying query access to Z from time to time. But we will show that the maximum number of queries that we make during this simulation of this protocol pi is at most the communication complexity of pi divided by the communication complexity of the gadget. So it won't be exactly the communication complexity of the gadget, but there will be some constants hidden there. But for this hard direction to work, we'll need some properties from the gadget. So this is why we can only prove lifting theorems for certain gadgets. Okay. So this is sort of the meta recipe. And so this in turn shows that this is like the decision tree complexity of F is times the communication complexity of G is upper bounded by CC of pi, and CC of pi for the best pi is CC of F composed C. Okay, so before telling you about our results, let me give some previous results in this context, just to put things in context. So Goose, Pitassi, and Watson in 2017, they proved a lifting theorem in the randomized setting. So this is BPP. So this is the two-sided error randomized setting. And they used a gadget which is known as the index gadget. So index gadget is a gadget which is asymmetric. So in the index gadget, Alice gets a pointer X, which is in M. You can think of it as a pointer from 1 to M. And Bob gets a really large string. Bob gets a string of length M. And the goal of the players is to find the exit bit of Y. So the index gadget outputs the index gadget on X comma Y is supposed to output Y at X. Okay, but if you look at the size of Alice, this is just logarithmic in M, but whereas size of Bob is exactly M. So compared to the size of Alice, Bob's inputs are exponentially larger. And this makes the hard direction of the lifting theorem somewhat easier. But for deterministic, so they also proved a earlier result which works for deterministic lift in the setting of deterministic lifting, which is a reinterpretation of an older result by Ras and McKinsey. But the Chattopadhyay et al. And Wu et al. Independently also proved that for a much smaller, much concise gadget known as the inner product gadget, we can get this similar lifting theorem, but in the deterministic setting. So the inner product gadget is where Alice and Bob gets two n-bit strings. Sorry. So it's where Alice gets an let's call it B. It gets B bit string X, and Bob gets a B bit string Y, and their goal is to compute the inner product of these two strings modulo 2. So you just take sigma xi yi and sum up to mod 2. Okay. So in the inner product gadget, both Alice and Bob have the similar sized inputs, whereas in the index, there was this asymmetry where Alice's inputs were tiny compared to Bob's inputs. And yeah, so what is the catch here? The catch here is that, like, we need, for these lifting theorems to work, the gadget, the size of the gadget has to be comparatively, it has to be like quite large in terms of the input length of F. So these results actually work for an index gadget, where index gadget on m bits, where m is some large polynomial in n, where f is an n-bit function. So if you are trying to lift the query complexity of an n-bit function, we need a gadget which is polynomial in the input size of f. And although on Alice's side this is only logarithmic, on Bob's side this is exactly polynomial. And this blow up is actually costly for some applications. But whereas the inner product gadget, they only need the number of bits in the inner product, in the individual inner products B to be somewhat large, something like 100 log n. Okay. There been so compared to the index gadget, the actual size of the inner product gadget is much lower in this lifting theorems. There have also been some recent improvements to the gadget size for the index gadget using connection to sunflower lemma from combinatorics, and maybe you've seen Ian's talk and using a different proof, m is like almost polynomial now, like almost linear now, but going beyond linear in the case of index gadget, or beyond logarithmic, smaller than logarithmic in the case of inner product gadget, is a challenging open problem. So in this context, our result addresses the natural next step. So we know we can prove deterministic lifting theorems with the inner product gadget, which is way smaller than index gadget, and this matters for many applications. So can we prove randomized lifting theorems also with inner product gadget? So in this work, we actually prove such randomized lifting theorems, which says that the BPP communication complexity of F composed with inner product is approximately equal to the decision tree, randomized decision tree complexity of F times the randomized communication complexity of inner product. And which for an inner product gadget on B bits is, sorry. Yeah. Yeah, I think it got disconnected. Yeah. Yes. And for an inner product gadget on B bits, this is theta of B, and we again need B to be some large constant times log in N. F is a function on N, capital N bits. Okay. But more importantly, our results also work for many more gadgets so these are gadgets which have this combinatorial property called exponentially small discrepancy. I'm not going to define it right now. I'll push it to the technical part of the thing. But the main takeaway message is that it shows that if you take a random function, if you sample a function at random from functions whose input is about like 100 log in size, then that random function acts as a good gadget. So a large family of functions G whose size is about 100 log n can be used as gadgets in both randomized and deterministic lifting theorems in this context. So as it says here, our results also work in a deterministic setting, and it also works for things more general than functions, total search problems, and things like Kashmir dozen relations, etc.
So Sajin, have you any advice how to think about intuitively about small discrepancy? Should I think about it as, even if I set fairly many, even if I fix fairly many input bits to the gadget to particular values, somehow the output is still fairly evenly distributed? Is that how to think about it?
So the bit fixings are only like bitfix, yeah, it has to work under bitfixings also, but usually you look at the rectangle, so G is on X cross Y, and you look at any kind of sub-rectangle, then the number of zeros and ones you see is sort of balanced.
So even under, not just under restrictions, but to like correlated subspaces somehow or whatever.
Correlated, yes, under any kind of distribution.
Mm-hmm.
Yeah. So yeah, so basically what we need is that like G sort of obfuscates the value of Z. So unless you have so much information on the on Xi and Yi, you wouldn't know what the value of G is. So if G is very biased, if G is like mostly zero, then maybe the players can communicate a few bits and decide that like G is like some constant. So we want G to be as unbiased as possible and as unbiased as possible and under many distributions. Yeah.
Mm-hmm. Thanks.
So yeah, so some applications of the lifting theorem. So it's been used to prove new separations between quantum and classical communication complexity, and also to prove like results in circuit complexity, and especially like to prove a variant of the KRW conjecture in this monotone and semi-monotone settings. Oh, interestingly enough, our results also simplify a randomized decision tree lower bound of Jairam and Mika. But the interesting thing is that it uses a lifting theorem to prove a randomized decision tree lower bound, and the earlier result used a different kind of lifting theorem. But because we are using the inner product gadget, we could like get that result as a simple corollary. Okay, so now yeah, I'd like to get into the high level overview of how we prove such a lifting theorem. So the easy direction is as obvious as the one we just saw earlier. It just follows that recipe. The hard direction is what we'll focus on. And this is not just restricted to the inner product gadget. We will mention some issues which are specific to the inner product gadget, but in general, this is sort of a meta recipe for proving the hard direction for like many other kinds of gadgets, like almost all gadgets that we use in deterministic or randomized lifting theorems. So as we saw earlier, like the hard direction is basically a simulation algorithm. Shouldn't be calling it algorithm. It's a simulation decision tree. So what the decision tree takes is that it takes this. So what we need to prove is that we, from a randomized protocol solving F compose C, we can come up with a randomized decision tree which solves F. Okay. So we are going to use this randomized protocol pi, which we assume is the best protocol solving F compose C, to build a randomized decision tree for T. But any randomized protocol pi can be thought of as a distribution of deterministic protocols pi sub r, where r is some fixing of the randomness used in the protocol. So we would actually be building the decision tree on the deterministic protocol, which is pi r. Okay. So, and the output of the decision tree, as we said, the one way to think of it, so the output is supposed to output also F of Z, but the more natural way to think about the output is like it's an output on the distribution of the leaves pi of this protocol pi, leaf small pi of this protocol pi. And we want this distribution, so I call this distribution TC. This is like it's also a similar, and like, this naming convention is from GPW from an earlier work. And we want to like show that this, like we want to build an algorithm so that this distribution is close to another nice distribution. So this nice distribution, which I call T-C, is the distribution of the leaves of this protocol phi are induced by the following distribution. So so the decision tree is supposed to find out f of z for some input z which is unknown. So z is not known to the decision tree, but we know what z is. So we define this distribution to be all strings x comma y which are uniform from the inverse of g inverse of c. So G here is, okay, so some notation. So G here is the gadget on the n copies of the gadget. Okay. So these are all the inputs which, so basically this is just basically saying that if you apply G1 on X1, Y1, you will get Z1 and so on and so forth. Gn on Xn, Yn would give you Zn. Okay, so we restrict our focus to only those inputs x, y, which produce z when applied with z. So and we want the output distribution of this simulation algorithm to be statistically close to this distribution. So why is this distribution good? Because if you think about it, like, so here I've like denoted the paths, the paths taken by xy, which are from g inverse of z in this color. So so we are fixing z to be some specific value in 0, 1 to the n. So because we are fixing z to be some specific value, the xy that produces c will only reach some subset of the leaves of this protocol. But these leaves which support this xy also compute, like, so on such xy, if these so at this leaf, because this is a deterministic protocol, there's some xy which is in G inverse of C, right? So whatever this protocol outputs on pi of xy, whatever the protocol outputs as the 0, 1 value must be the value of f compose G on Z with high probability. Okay. So if we were not doing the randomized lifting theorem, if we were doing a deterministic lifting theorem, then if we can find at least one path which is always supported by an xy from G inverse C, then and then the leaf that we reach also contains such an xy, then we know that the output of the protocol has to be f of z, because the output of the protocol is supposed to include f compose G n of x comma y, and g to the n of x comma y is z, so f of z should be the correct output. It cannot be, like, because it's a deterministic protocol, there cannot be two answers. So if we can follow this, so in the deterministic setting, if we can at least follow one path where we always have at least one xy which is from G inverse of C, then the leaf that we reach would tell us the correct value of f of c. And in the randomized setting, we want to say that, okay, so if somehow we had access to z, then this is the distribution the randomized protocol would have taken, and we want to simulate this distribution. Okay. The problem is that, like, we don't know what z is. So the decision tree algorithm, which is trying to mimic this distribution, have no idea what z is. So this seems like an impossible task. So this is where, like, the properties, the special properties of the gadget that we use come into play. Okay. So let me just give you, like, and give you some intuition by starting with the the simplest node in the protocol. So this is the root node. So this is the first node in the protocol. So here, like, and I've taken the gadget to be the index gadget. So X is all M, all strings of the form M to the N, and Y is all strings of the form 0, 1 to the M, whole to the N. Okay. So because the players haven't started communicating, they have not eliminated any of the inputs as their possible inputs. So Alice can get any bunch of N pointers, and Bob can get any 0, 1 string of length M. Okay. And what is our goal here? So we want to sample the next node. So like, remember in the simulation algorithm, our goal was to trace a path, sample a path according to the distribution XY, which is uniform from G inverse of C. So to do that iteratively, we would like to sample the next node in this among the children of this root node according to this distribution. Okay. So here I claim that, okay, but we don't know what Z is. But if you look at the index gadget and you look at any Z, I claim that if you look at this particular distribution, that is XY from G inverse of C, the X marginal of X comma Y is just uniform on M to the N. Sorry, this should not be 0, 1. Sorry. Yeah, I'm using my iPad to point at things, and sometimes it disconnects. Sorry. Can you see my screen again?
Yes, we can see your screen.
So this is M to the N. So X is any of the M to the N pointers. So for example, let's take M to be 2 bits. So you have 2 locations in Y, and the pointer can be either location 1 or location 2, and N to be 2. So there are 2 blocks in X and 2 blocks in Y. So, and let's fix the output of the gadget and the index gadget to be 1, 0. Okay. And now let's look at the distribution XY, which is from G inverse of 1, 0. So for that, to nicely describe this set of inputs XY, which are from G inverse of 1, 0, divide it into like it's inputs based on various values of X. So let's say X is 1, 1. So X is 1, 1. What that means is that we are looking, so if X is 1, 1, Z1 is basically Y at location 1. Location 1, 1. So if you think of Alice's input as X1, X2, and Bob's input as Y11, Y12, Y21, Y22, then X, by setting X to be the first pointer in the first block and X2 to be the first pointer in the second block as well, we are setting Z1 to be the first bit of the first block of Y, and Z2 to be the first bit of the second block of Y. So this is, and because we have fixed Z to be 1, 0, so this means that this bit has to be 1, the next bit could be anything, and this bit has to be 0, the next bit could be anything. And similarly, when we set X to be 1, 1, 2, what this means is that then Z1 is just again Y11, 1, but Z2 is Y22. So this means that this bit has to be fixed to 1, this can be anything, this can be anything, and this has to be 0. But now, and the remaining 2 inputs describe all the inputs X comma Y in G inverse of 1, 0. Yeah. But now if you look at any particular X, the number of Y's for which X comma Y is in G inverse of 1, 0 is exactly 4, right? Because you can turn this bit into either 0, 1 or this bit into either 0, 1. So for any particular y, the number of y's that are valid inputs which produce 1, 0 as the output of the gadget is exactly 4. So now if you look at, so if you sample an xy from this distribution and you look at the probability of a particular x in the distribution, so let's say the probability of x equal to 1, 1 is the same as the probability of x equal to 1, 2, right? And in fact, all these probabilities are the same. So this shows that, like, just by like a simple proof, it shows that at the root node, at least the x marginals of x comma y for any particular g inverse of z is equal to the uniform distribution on m to the n. Okay, so this gives us a chance to sample the next bit according to this distribution x comma y, this bold x comma y, which is from g inverse of z. So how is that? So basically, like, we are at this node. Let's assume that at the root node Alice speaks. So Alice communicates some information on her input and divides her input into 2 parts, x0 and x1. So here she sends the 0 bit and here she sends the 1 bit. And this, based on this partition, she partitions it into 2 nodes. So now we will choose the left child with the probability x0 over x and right child with the probability x1 over x. So because so this is like, if you sample an x from x, the probability that this x goes into x0 is exactly equal to this, right? So we are sampling the next bit as if x was sampled uniformly at random from capital X. And this claim that the marginals of the target distribution, which is unknown to us because we don't know what z is, on x is equal to uniform distribution x. This is the right distribution. Okay, so at least at the root node, by doing this kind of sampling, so what would our decision tree do? The meta decision tree, it would just use its internal randomness to flip some coins and flip a bias coin whose bias is exactly this, and based on the outcome, choose one of these descendant nodes as the next bit. So remember, the end goal of our simulation theorem is to like reach a node, reach a leaf of this protocol. So we've gone from root to one child below. Okay, so, and in general, this might not be true for other rectangles. So the more and more the players communicate, this property could go away. But for a carefully chosen gadget, we can prove a theorem, like in all these lifting theorems, we prove a theorem known as the uniform marginals, which says that, like, look at any kind of rectangle in the protocol. So if we are at some intermediate node in this protocol, we can, that node has an associated rectangle. If that rectangle has somewhat of a structure, so we'll define what the structure means. But if it is like very structured, then we can say that the x marginal of x comma y for any g inverse of z is close to uniform x, and y marginal of x comma y and g inverse of z is close to uniform on y. So basically, we are saying that for this gadget, for any kind of rectangle which is structured, if you look at a typical x and color the value of x comma y, so you look at a particular, so these are all y's, and you color a particular x comma y by the gadget output of g on x comma y. So here, like, I'm assuming there are like 4 different gadget outputs possible. So if you look at a typical x for a good gadget on a good rectangle, then the the device that belong to a particular Z. So here we are looking at like all these Y's which are in the same color implies that if you apply G to the N on X comma Y, you get the same Z. So if you like cluster these Y's based on the gadget output, then all these clusters are of the same size. So this is like sort of what we had for the root node, but because of some pseudo-random properties of the gadget, we'll also be able to show this for interesting rectangles. Okay. So if you, in particular, if you rearrange the Y's, you can see that like there are like 3 Y's which give one particular input, which is purple, and the 3 other which give something else. So basically, if you cluster a row of X by the gadget output based on the Y's, then all these clusters are the same size, and similarly for a typical Y. Okay, so in general, for any rectangle which has this uniform marginals property, we can carry out this sampling algorithm. Sorry. So what would we do? So suppose XY is any structured rectangle, and sorry, this is going in the wrong direction. Sorry. For some reason, it's skipping. Sorry. Let me just start it. Yeah. Can you see this now?
We can see the opening slide.
Yes. Yeah, so now for any structured rectangle, we can use the same philosophy to sample a descendant according to this target distribution that we need. So for any structured rectangle, the uniform marginals lemma tells you that for any C, the X marginal of XY sampled from G inverse of C is uniform on the X inputs, and Y marginal is on the uniform on the Y inputs. So in particular, in a node where Alice splits in XY into X0 and X1, we will sample the left child with probability X0 over X and right child with probability X1 over X. And so now I'll define what structured means, what pseudo-random properties have we, what pseudo-random property we will use for the inner product gadget, also the other gadgets of low discrepancy. So to define this, we need this notion of density. So let's assume that like we work in the inner product gadget. So Alice's inputs and Bob's inputs are bit strings of n bit strings of length b. So let's say X is a random variable over this universe. So we say that X is a dense random variable if the min-entropy, so if you take any subset of the blocks, so we think of the inputs as blocks. So we think of each of these vectors x1 to xn, each of these things as a block of b bits. So if you look at any subset of blocks I, then you look at the min entropy of that block. So the maximum sort of min entropy that block I can have is I times the number of bits in that block. Okay. So this says that if it is delta dense, then it's at least some delta fraction of that. So think of delta as some large constant which is less than 1, like 0.9 or 0.8. Less than 1, but larger than half. So this says that if you look at a bunch of IB bits, the maximum min entropy could have been IB, but under X, it still has considerably large min entropy, which is something like 0.9. And this happens no matter what subset of blocks you're looking at. Okay. So this is going to be our measure. Oh, and what is Xi? Xi is just the induced, so X is the uniform distribution on the inputs from X, and Xi is the induced distribution obtained by projecting this X onto the blocks I. Okay. And we call this rectangle structured if X and Y are both delta dense. And for this talk, you could assume that delta is something like 0.8 or 0.9. Okay. So to give some intuition of like why we use min entropy, let me go back to the index gadget. So in the index gadget, Alice gets n pointers, which are in 1 to m. So to represent a number in 1 to m, you just need log m bits. So Alice's inputs are over these kind of strings, which you can equivalently think of as m to the n. And Bob's inputs are much larger. They're bit strings of length mn. So in lifting theorems, which use index as a gadget, the structured rectangles are slightly different. So those theorems only need X to be delta dense and Y is large. Okay. And they need that the number of bits in a block is a large polynomial in n. But before defining what Y large is, let's consider this very simple protocol where Bob only reveals bits. So Bob has some input from small y from this capital Y, and he only reveals bits of this input. So after some bit amount of communication, the set of inputs supported by some node of Bob would look something like this. So you don't know what the inputs in white are, but the inputs in red are the bits that Bob communicated. Maybe this is set to 0, this is set to 1, this is set to 0, this is set to 0, so on and so forth. But the total communication in the protocol is only something like n log n, right? Because the naive protocol would take this long. So any function on n bits has a decision tree of cost n. So if you plug in that decision tree, and because the index gadget has communication complexity log m, the communication complexity of the protocol can be assumed to be smaller than n log n. Actually n log m, but m is some polynomial in n. So this is some 256 n log m. So even if we are at a leaf node or a near leaf node, inside a block, only up to n, something like n log n bits are fixed. The remaining bits, if Alice indexes into one of these bits, these can be, one of these green bits can be either 0 or 1, and it's going to be 0 or 1 equally likely in this very simple model where Bob only communicated bits of his input. In general, Bob could send very complicated messages. But now, because X is dense, what does it imply? So X is delta dense. So we know that Alice's input X is delta dense. So this in particular means that, so if you look at the first pointer, which we call X1, the number of possibilities for that first pointer is going to be, because the min entropy of X1 is going to be at least, so H infinity of X1 is going to be at least delta log m, because the number of bits in a block of Alice is log m. And the definition of density says that it's at least delta times of that log m. Because the min entropy is this much, there must be at least m to the delta different values for that particular x1. So if you look at that m to the delta, and m is very large and delta is not that small, delta is something like 0.9. So m is something like n to the 256 and delta is something like 0.9. This is much larger than n log n, right? So the many different locations, so most of the locations accessed by x1 would be these green pointers, right? So only a small fraction of locations would be fixed or biased. So in this case where Bob communicates bits, it's fixed, but in general, you could say that only a few number of bits would be biased. Okay, but this is just for one block. So this is why we need this density definition to extend over all subset of blocks I. So now if we fix x1 to be some particular value alpha 1, which is, let's say, this one, because we are talking about min entropy, the remaining inputs, so this x restricted to x1 equal to alpha 1 is also delta dense. So x2 also has m to the delta locations, and only like a small fraction of that can be bad locations. So in general, this tells you that if you look at a particular string x and x, the possibility that like all of the individual blocks are pointing to good locations in y or unbiased locations in y, that probability is very high. Or if you look at a particular a typical x and you sample y uniformly at random from y, then you're going to get any z equally likely. So if x1 points to one of the unbiased locations in y, if you sample a y uniformly at random from y, that the value of x1 at that y1 location would be equally likely to be 0 or 1, right? So this is sort of the reason we go for min entropy and this blockwise definition of min entropy, because you can keep fixing things and so it's not a product distribution. It's not like each xi has m to the delta different values independent of the other ones, but for each fixing of x1, there are m to the delta values of x2, and for each fixing of x1, x2, there are m to the delta values of x3, and so on and so forth. Okay. So now, yeah. So this is sort of the high level idea of the proving uniform marginals just using this sort of pseudo random properties. And now so we saw that like whenever we have a structured rectangle in the simulation, so we are at a node which is already structured, then in our simulation, we can sample the next bit using our strategy for the root node. But as the players communicate more and more bits, a rectangle which was structured could stop being structured. Okay. So we consider this example like this the node where Alice speaks, and based on communication of Alice, x gets split into x0 and x1. So x was delta dense, and it could be that x0 is not delta dense. So, but we can still assume that it's considerably dense. Okay, uniform marginals are still true, but it's not delta dense. So we would like to move from a structured rectangle into another structured rectangle. So we don't want to lose the structure. So we want to restore density. So to restore density, we are going to use querying. So far, we have only used randomness. So our decision tree had access to internal randomness, also had access to query, also had query access to the input Z, right? And so here to restore density, we are going to use query. So what are we going to do? We're going to find, we know that x0 is not delta dense. So there must be some subset I of n and an alpha I witnessing a witness alpha I such that the probability of xi being alpha I is larger than, strictly larger than 2 to the minus delta ib. Or this is equivalent to saying that h infinity of xi is strictly less than delta ib. So this is from definition of min entropy. Okay, so so if min entropy is low, means that there is some event which is of very high probability, and this high probability is decided by delta. But if we find, if we don't just go for any I, if we find a maximal such I, not the maximum, a maximal I, then, and we fix xi to be some alpha I which witnesses this min entropy loss, then we can say that the rest of xi, the rest of x is delta dense. So x dash, which is obtained by fixing xi equal to alpha I, is delta dense in n minus I. So we had some I, which is the maximal thing, and we fixed this xi equal to some alpha, and on n minus I we got a part which is delta dense. So now we would like to only think about gadget output on those blocks. So what we do is we query I. At this point we query I and obtain the query answer zi on these locations. And once we obtain this query answers, we need to make sure that the set of inputs phi that we are working with is consistent with the query answer. So we have set xi to be alpha I, and we would only keep those y in y for which g to the I at alpha I yi gives ci. So this ensures consistency with query answer. Okay, so I think, yeah. So yeah, I'll just go over this one more slide, and then maybe, I think I'm over 1 hour time at this point.
Sure, but it's up to you to structure the talk as you wish. I mean, we're listening. So if you want to go a few minutes,
okay,
a few minutes more to wrap up, that's perfectly fine.
Okay, so yeah, I'll take 5 more minutes then. Thank you. So here, yeah, in density restoration, what have we achieved? So we know that whenever we did density restoration, there was some set of blocks I where the min entropy dropped below this threshold. But initially we started with the root node where the min entropy of xi was exactly IB bits. So intuitively, for min entropy to drop to this threshold, there must have been a lot of communication. How much? Precisely this much. Okay. And now we are querying I and obtaining CI. So remember that the simulation algorithm, the decision tree that we are building should have query complexity, which is the communication complexity of pi divided by the communication complexity of G, right? So we need to control the query complexity somehow. So, but because of this design, we are querying a set of blocks I only when a considerable amount of information has been leaked about those bits. So in particular, if you think this, we are querying a block I if at least I bits are we make I queries for every 1 minus delta IB bits communicated. Right? So we can say that the query complexity is comparable to the communication complexity divided by 1 minus delta B. So for every this amount of communication, this is the number of queries we make. So the total communication is CC of pi. So then total queries that we make would be 1 minus delta times p divided CC of pi divided by 1 minus delta times p. Okay. So this allows us to control the query complexity. Yeah, so now I think I'll stop at this point and continue with the, so far I've not delved into any details about index versus inner product. So we'll see how to deal with, there's some issues with both inner product and index, and yeah, there's some other technical details. So yeah, I'll also like wrap up the simulation algorithm once we discuss these issues.
Thank you. So, and do you have any like for people tuning out after the first half, any concluding slides like future directions or any conclusions or?
Yeah, yeah. So let me just skip this. So this is. Yeah, so yeah, there are some really interesting open problems from this direction. So one obvious question is to get like gadgets of smaller size. So in particular, like an interesting question is to see if we can get gadgets of size exactly log n. So in the case of index gadget, the GPW result needed an index gadget of size n to the 256. Or some large constant like that. And recently, based on improvements of on sunflower lemma, the gadget size was reduced to almost a linear in n to the 1 plus epsilon almost. But the connection, the improvements based on sunflower lemma is used to show some sort of a dispersive property for the gadget. So it's not clear how to show that dispersive property, for example, for inner product, and it's not clear how to extend it to the randomized setting. So in the randomized setting, we need to show that the gadget is sort of an extractor. So we want to show that if you sample an x and y, so if you look at a typical x and typical y, every c is equally likely. This is an extractor property. But in the deterministic setting, you want to say that, okay, for a typical x and by choosing a typical x and typical y, you would get any kind of c. All c's in 0 under n are possible. So we don't know how to prove a extractor property using these techniques. So it's not clear whether either in the deterministic setting can we improve the inner product gadget to log n, or in the randomized setting can be either for index or in inner product use these ideas from combinatorics. So the other question is like it's more general and open-ended. So here we are lifting randomized decision tree complexity into randomized communication complexity. How about like we go beyond communication complexity? So one avenue is to do lifting for information complexity. This is not known and this is challenging. Another related but maybe easier goal is to try and prove DAG-like lifting theorems for DAG-like protocols using inner product gadget. So currently we know deterministic DAG-like lifting for index gadget, but those results don't work in the case of inner product. So yeah, it would be interesting to see if we can get DAG-like lifting using inner product. And another natural question is like here we show that any gadget of exponentially small any function of exponentially small discrepancy can be used as a gadget. Can we prove it for even larger class of gadgets? So one example would be gadgets of high information complexity or discrepancy, which is not exponentially small in the input size. So, and another question. So here, all these lifting theorems assume like this uniform marginals and other things work for product distributions, and in general, like if you have non-product distributions on XY, then we don't know how to prove lifting theorems. Yeah, and obtaining smaller gadgets and lifting to information complexity and other things would have breakthrough results in related areas in circuit complexity and communication. Yeah, that's it. Thank you.
Thank you so much, Sajin. That's a nice collection of open problems and a very nice overview. And we're looking forward to more after the break. I had two sort of maybe slightly orthogonal questions. So one was, has there been any work on, I mean, this is somewhat inspired by your initial example of getting set disjointness as a lifting of with the so would it make sense, or has it been considered to somehow work on gadgets that only work for particular f, where you like assume something about your function? Would it somehow help? Or is it the case that we always, because it's like all of these lifting theorems, they basically just hide the inputs, and then that's why they work for relations and really anything, right?
Yeah. And that's why we are unable to push the gadget size further down. Like, so there've been the specific functions. Yeah, I'm not aware of any such like lifting theorems which.
Yeah, no, it's more like
Yeah.
I was just sort of a naive question, really. Another thing that you stressed in the beginning also, that our gadgets always lift single bits. Like, could it conceivably be a way of working on the trade-offs that you have some kind of, you know, gadget that is, I don't know, some error correcting code or something that sort of lift to multi-bits outputs, and that this would somehow be helpful?
Oh yeah, this is definitely helpful, especially in proof complexity. So in our joint work, like with Mika and Tony and Ian, where we actually had to prove lifting with multi-output gadgets, because we were like lifting block width. So this is an interesting question, and you can do deterministic lifting and DAG-like lifting with multi-output gadgets.
So the answer is yes, and this has been done. And the paper you're referring to is this non-automatability of cutting planes?
Yeah. Yes, that's right.
Right, right. I guess I should have remembered. Sorry about that. Any other questions before we take a break? Anyone? Otherwise, I think we'll just take a break and be back in a few minutes. Yeah. So we are back after the break, and Sajin will continue speaking about density restoration. Please.
So yeah, so in general, like density restoration allows us to get uniform marginals on the blocks outside I, and the way, like, because we are using this density measure, we also know that we do density restoration and querying only when we have accounted for enough communication from the players. So there's a nice way to balance query complexity in terms of communication complexity and the number of bits revealed per block, which for index and inner product corresponds to like the communication complexity. But there's a small problem. So whenever we query I and obtain Zi, we want to like update the set Y of inputs so that the set Y is consistent with the query answer. So what we have done is like we have essentially, like on the blocks I, we have set Xi to be some alpha I. Okay, if this was the index gadget, let's say this alpha is some alpha 1, alpha 2, alpha 3, alpha 7. So I is 1, 2, 3, 7. So this is like fixing Z1 to be Y alpha 1, right? Z2 to be Y alpha 2. Sorry, not Y alpha 2, but the first block of Y at alpha 1, Y1 alpha 1. Z2 is Y2 alpha 2, so on and so forth. Z7 is Y7 alpha 7. So once we query, like maybe like we get the answer that Z1 is 0, Z2 is 1. So then what we need to ensure is that we only keep those Y where Y1 alpha 1 is 0. So this suddenly removes quite a lot of Y's from our set of inputs Y. And we also want to make sure, so by doing density restoration, we ensure that X on n minus I is delta dense. And Y was originally delta dense on all blocks. But by doing this conditioning, we are removing some set of Y's, and we don't want this set of Y's to affect the density of Y on n minus I. So after cleanup, we ideally would like to have the situation where X on n minus I and n minus I and Y on n minus I has delta density. So, so whenever we, but whenever we are set like doing this conditioning, this typically reveals about like I bits of information. So Zi is a bit string of length I, and this conditioning, like on average, would reveal I bits. But in reality, two things could happen. So one is called leaking. So leaking is the case where for some particular value of alpha I, which is this heavy value that's fixed, and so for some particular value of Zi, this conditioning that Xi, Yi is Zi reveals more than I bits. And this is bad for us because this would destroy the density of Y on the remaining blocks, and also would tamper with our accounting. So we want to say that the number of queries that we make is proportional to communication. So the amount of information that's revealed on the inputs of the players should somehow be related to communication. So if we reveal I bits of information, that's fine because I is already related to communication divided by theta of B. But if we reveal like arbitrarily larger than that, then we are in trouble. This is other problem that is known as sparsifying. So that doesn't happen for the index gadget, and that is something particular to the inner product gadget. So here, what happens is that by conditioning on this particular value of Zi, we are destroying the density of Y on this n minus I blocks. Okay. In particular, like so let me just tell you like why this is not a problem with index gadget. So in index gadget, a typical block of Y is of size, let's say n to the 4, or I mean, it's at least n to the 4. It's a large polynomial in n. And then amount of information. So if it's not leaking, we are revealing about I bits of information, right? So even if that all of these I bits of information go into a single block of Y on n minus I, this only covers a small, so I've marked those positions by red. This only covers a small portion of the bits in that block. Right. So if we had this other concern that leaking, where I bits of query answer reveal more than I bits of information. If that doesn't happen, then a query answer only reveals I bits. But and in case of the index gadget, this revealing I bits onto even a single block is not a problem, because a block is larger than the maximum number of queries the decision tree is going to make.
And here we're arguing about the huge asymmetry between Alice and Bob, right? So like, even if I tell you lots and lots of information about one of Bob's blocks, that sort of, well, Alice's index is probably somewhere else anyway. So like Bob could, information from Bob is not very interesting somehow.
Exactly. So yeah, as you said, like more formally, because like we have conditioned on xi equal to alpha, we know that x, if you look at x on n minus I, it has high mean entropy. So any particular like block inside x would see like many positions inside y. So even if like many of them are fixed due to this sparsifying, it's still not a problem. That's still like a tiny fraction, n over something like n to the 256. And this is what we will add that to error, this kind of small deviations. But for the inner product gadget, the size B, the number of bits in the block is only about like 100 log n. And in like, depending on where we are in the query algorithm, it could be that I is something like, I don't know, much larger than log n, let's say log square n, or it could even be n. So such a large I, if we are revealing all the information released from Zi into a single block of inner product, that entire block could get fixed. The I can be larger than B. I can be, in fact, much, much larger than B. So here, then we have no like hope of fixing uniform marginals on n minus A anymore. So we need to like make sure that sparsifying doesn't happen. We need to make sure that leaking doesn't happen with both inner product and index, because if it's leaking, then we have no way of accounting for query complexity in terms of communication complexity. But once we ensure that query answers only reveal I bits, we still need to do extra work to make sure that there are no sparsifying values in the inner product gadget. For index, you don't have to do this. Okay, so this is our main contribution. So we call an input X leaking if there is some subset of blocks I and a query answer Zi, such that the probability, if you condition on this particular gadget output being the output in this xi yi rectangle, then that probability is less than 2 to the I minus 1. So information is like measured exponential, and like it's in this probability. Oh, so this not I 2 to the, so this is 1 over 2 to the I minus 1. Sorry. So this is like saying that it's revealing more than I minus 1 bits of information. That minus 1 is a small technicality. So X is leaking if the query answer reveals more than I bits of information. And X is epsilon sparsifying if there exists a set of blocks and a query answer such that the sum, the density of Y outside these queried blocks is lost. So we initially had that it was delta Y dense. And now because of this conditioning, the density is lost. So for index, an X is dangerous if it's leaking, sparsifying doesn't matter. And for inner product, what we need to show that we need to avoid inputs X's or in particular, the heavy values that come from these X's, which are dangerous. So an X is epsilon dangerous either if it's epsilon sparsifying or it's leaking. So our main lemma says that if your XY rectangle is 0.9 dense and 0.8 dense respectively, so there's some slight asymmetry in this density of X and Y, but it doesn't have to be this particular constant. But for simplicity, let's assume that it's 0.9 and 0.8. Then the probability of a particular X and X, taking a dangerous value is bounded by 2 to the omega minus omega of b. And b here is the gadget size. So for b here, for the inner product is 2 to the minus something like 100 log n, or this is 1 over poly n. So this is very small.
And this would be one of the places where, which stops you from pushing the gadget size lower, or?
Yes, yes. Yeah, very good point. Indeed, like, so,
will you have
so
to like, you'll have to union bound over these events in the end somehow, or?
Yes, exactly. Yeah, exactly. That's the problem. So we'll have to union bound. So these definitions work with all kinds of subsets I and all kinds of values zi. So you need, like, usually you do this by union bounding. So you say like x is epsilon sparsifying if there exists one of them. So you'd show that the probability that x is sparsifying for a particular I and zi is very low, and then you take a union bound over this. And any of these probabilities have to be something like 2 to the minus omega b, because the gadget is only like 3 bits in length. It cannot be smaller than, way smaller than that. So yeah, and we need 2 to the b to be much smaller than at least n, because our union bonds will go over like, yeah, at least n things. So you want this probability to be like 1 over poly n, so that even if you sum over like n different things, it's still 1 over poly n. Yeah.
I see. Thanks.
Yeah. Yeah. So now, assuming that we have this, like we've proved this main lemma, let's revisit how we do simulations. So especially like how do we regain structure? So earlier we showed that we, in the, at least in the deterministic setting, the way to regain structure is like you find a maximal I that witnesses the loss of density, and then fix that xi to be some alpha I, and then query. But here we need to make sure that before we do any of that, we are not taking a value that is dangerous. So later on, like the conditioning won't either reveal more than I bits, or it would not like destroy the density of y. So what we do is like we take an rectangle that is structured xy, and then we, before like sampling the next bit, we first condition on x not taking an epsilon dangerous value. But because of the main lemma, we know that this probability that x is not taking an epsilon dangerous value is very high. It's something like 1 minus 1 over poly n. So almost like always x would not be taking a dangerous value. So conditioning on this doesn't destroy density by much. It's a very small reduction in density. So you're only like removing a small number of x's. And now, now we continue as before. So we assume that, okay, if the next bit of Alice destroys density of x0, we will just then restore the density by the same argument. But because we have removed all dangerous values from x, we know that like this alpha I is from some xi, right? So it's like alpha is a value for xi. So this particular xi is not dangerous. So the x that it came from is not dangerous. So for this particular xi is also not dangerous. It's not leaking. It's not sparsifying. So we know that like this query answer will only like reveal I bits of information, and we'll also be sure that y on n minus I is dense. Okay. So because of these two things, we know that like y is dense on n minus I, density would decrease by a bit, but it's still considerably dense. And we already know from the earlier argument that if you fix I to be one of the values which witnesses the loss in mean entropy, the X part is already dense in n minus I. So if you look at the restricted, the unqueried bits, so which are n minus I in X versus n minus I in Y, those parts have density delta X and delta Y minus some epsilon. So now on those parts, you have uniform marginals. And this is something you want to do, right? Because like now from now on, we are not going to think about I, because we have already queried Zi and we know the query answers. We can just focus on the remaining blocks, and we want uniform marginals on the remaining blocks. So by avoiding dangerous values, we ensure density on Y, and the earlier argument already ensures density on X, and this gives us uniform marginals on the unqueried blocks.
And this is somehow a big part of the magic, no? Because it's like I was thinking about this, that once you find this alpha I value that is dangerous and just commit to it on Alice's side, like, yeah, I mean, a priori, like everything could break, no? But you somehow then miraculously you recover your uniform marginals and you just go on and work on a smaller set of inputs.
Oh yeah, so that's an interesting point. So you're right in the sense that, like, yeah, any path that would have taken us to an alpha I which was dangerous would have completely destroyed our simulation algorithm. Most likely we would have had to abort our simulation algorithm. So I did not meant like bring this up explicitly, but the decision tree that we built from the randomized protocol on some paths would decide to give up. It would just say, like, we don't know the answer, like too much information has been revealed in too little rounds. So if you go to such an alpha I, that would happen. So the interesting thing is that, okay, so if you look at a particular rectangle XY that is structured, the bad x's, which are these dangerous x's, are a tiny fraction, right? So they are only like 1 over poly of the whole thing because of the earlier lemma. So the probability that your simulation would have gone into one of them, because your simulation is always like sampling X uniformly at random, the probability of gone into one of them is like only 1 over poly. So that is something you're adding to the error. So this is another problem with the randomized lifting theorems. So at each step, you're gathering some error. And this error also has to add up to something small at the end. So there's a union bound over the steps of the randomized algorithm. So this is where, like, this is one part where we push this thing into the error. So we say that, okay, yeah, you could have gone down that path where you would have taken an dangerous value, but that probability is only 1 over poly n. So you would, like, okay, this is where in the high level overview, I mentioned that the leaves that we sample using the decision tree won't exactly be the leaves that we would have sampled if we were sampling from XY, which is uniform over G inverse of C. It's only statistically close to that distribution. So this distribution, these two distributions, TC, T dash C, which is done by our simulation algorithm, and TC, which is what is this is the XY, which is uniform random over G inverse of C. These distributions are only statistically close. So in basically their total variation distance is 1 over poly n. And this total variation distance comes from all these kind of errors that we accumulate. So one thing is you have a message of m bits, which has probability much less than 2 to the minus m. So that sort of a message would reveal too much information in too little, like, bits. So you would ignore those kind of messages. So you would like just ignore those kind of transcripts. Although this TC would sample them. The other places like these dangerous values. There are dangerous values X, Y, which would appear in TC, and there would be leaves corresponding to that they would have sampled, which you might not sample in the simulation algorithm. So all these things you are like pushing under the carpet, and you're saying that all of these events are some 1 over poly in n, and this poly is large enough, and we only run for our simulation algorithm only runs for CC of pi, and CC of pi is at most some n log n. So you add up all these 1 over poly in n over these n log n steps, you still have an error which is 1 over poly in n. So you're fine. Yeah, definitely. So yeah, this is one of the reasons it's hard for information. This kind of union bound over errors, it's not, it doesn't work. Yeah. So so this was like the fix. So we're using this technical lemma. We sort of push dangerous values into like the paths taken by dangerous values into our error probability, potentially. So just following up on this. So the density restoration argument that I presented earlier was for deterministic lifting. So there you only need to so the goal is to go through the nodes of this protocol and maintain that at any node that you're at, you have at least one XY, which is from F inverse of C. But in the randomized protocol, you have to sample the next node according to the correct probability. We want our sampling distribution T-C to be close to TZ, which is uniform over C inverse of C. So here, the way to do density restoration is different. So here you take X, you first find the maximal I1 where H infinity of Xi1 is less than delta I1B. So first has no specific meaning. You can just choose any maximal set I1. And now you set X1 to be all those X's where Xi1 is alpha I1. And alpha I1 is a witnessing value in the sense that alpha I1 witnesses that probably that H infinity of Xi1 is less than delta IB. Okay, but once you have gotten this part, you don't stop. You don't just sample, you don't restrict yourself to that set and continue. What you do is like you set X to be everything but X1. So you remove things which were already in X1, and then X minus X1 is the new X. And if this X minus X1 has delta density, you don't do anything, you just stop there. Otherwise, if it also loses delta density, you find a maximal set in that new X and an associated value, and set X2 to be this new X condition on Xi2 equal to X alpha I2. So this, in terms of this original X, is just basically, it's saying that X is, this new set X is basically X conditioned on Xi1 not equal to alpha 1 and Xi2 equals to alpha I2. Yeah. So here we are like excluding everything from X1. So we'll only have those X's where Xi1 is different from alpha 1. And you do this until like either the set XL becomes too small, or you do until the remaining set X minus XL becomes dense.
Wait, can you explain again why we do this?
Oh, so in the randomized protocol, we need to like ensure that we are following the distribution of TC, right? So we had this distribution, which is xy sampled uniformly at random from G inverse of C. And because of uniform marginals, we knew that like for xy, which is structured, x would be the marginal of this distribution on x would be the same as uniform on x, right? So the right probability, like, so if we only focus on x1, that is like saying that we are only following the paths which would have ended up in x1. But we should actually follow a path xi with probability xi over x, right? Does that make sense?
It makes total sense. It actually, yeah, I this was connected to one thing I was wondering about previously, but I phrased the question poorly. So this makes total sense. Yes.
Yeah. So, and we continue until like either this set is too small or x minus xl is delta dense. Okay. And then we sample xi with probability xi over x, so that we still have this property that we are going according to the distribution where we are uniform over x. Yes. So now we'll revisit the simulation algorithm with these modifications. So our simulation algorithm will try to find a path from the root of the protocol. And remember that we are in the deterministic setting. So we've already sampled the random part of pi using the randomness of the decision tree and fixed the randomness. So we get a deterministic protocol pi r. And in this deterministic protocol, we are going to start from the root and trace a path all the way until one leaf. Not exactly trace, but sample a path. And to do this, we are going to maintain, like at every node, we're going to maintain some invariance. Every node that we sample, we are going to maintain some invariance. So the first invariant is like a restriction, some kind of bookkeeping to record our queries and query answers so far. So it's just basically a value on 0, 1, star to the n. So any coordinate. So if let's say if row 1 is 0 and row 2 is 1 and row 3 is star, row 4 is star, what that means is that we queried Z1 and the answer was 0. We queried Z2, the answer was 1. We have not queried Z3 or Z4. So by looking at this restriction, the fixed coordinate tell us which coordinates were queried and what the query answer was, and the free coordinates tell you what the unqueried answers are. And if you project row to the fixed thing, those are the query answers. And we also maintain that we are always at a rectangle. So this node has some associated rectangle. Let's call it x pi cross y pi. But we focus on a sub-rectangle of this x pi y pi, which is row T structured. So what does that mean? So it means that we are only thinking about x restricted to the free coordinates of row, or x restricted to the unqueried parts. And x restricted to these unqueried parts is delta dense, and y restricted to this unqueried part is delta dense. So as I said, we will use a different threshold for x and different threshold for y, but that's a technicality. And these thresholds have to sum up to something larger than 1 point something, but that's not, yeah, think of them as like 0.9 and 0.8. So we're going to maintain this invariance. This is our goal.
And when you say asymmetric, you mean that you want you're maintaining higher density for the person who is about to speak, or?
If no, actually, like we are only looking for even with inner product, we are only
because otherwise, why can't I just switch for inner product?
Yeah, so I could, yeah, because of the symmetry. Like, sorry, what I wanted to say is that for for inner product, it would be based on the person who is speaking. So the way we define dangerous values, so they don't like, we need some kind of gap. We say that, okay, we take an y that is delta dense, and we say that a value is dangerous if it reduces the mean entropy by delta minus epsilon. So by conditioning on x taking non-dangerous values, we will not get that y has density delta, but we'll only get that y has density delta minus epsilon. So if Alice is speaking, yes, y would have lower density, and Bob speaking, Alice would have lower density, because then we will condition on y not taking a dangerous value for x, and as a consequence, x would not have exactly density delta x, but delta x minus epsilon. That's right. Exactly.
Okay.
Yeah. So now to combine everything together, we also need this uniform marginals lemma, without which our original strategy would not work, right? So we knew the uniform marginals lemma was known for index gadget, but it was also known for inner product gadget from long time ago, by this paper by Guzlov, Mecca, Watson, and Zuckerman. So where they say that if you take the inner product gadget on 1000 log n bits, and if x and y are row tau structured, where this tau is like 1.2 or something, then for any gadget output z that is consistent with the query answers so far, then for any such c, the distribution, the target distribution that we are trying to emulate, which is this one, this is what we call TZ, has its marginals are not uniform over x and y precisely, but they're statistically close to x and y, uniform over x and y. So what that means is that, okay, so if we go back to that picture that I was showing you earlier, like in what uniform marginal says is that for a typical x, if you cluster the y's based on the gadget output, so maybe all these y's are one gadget output and these y's are one another gadget output. For a typical x, this would be almost equal. But for some x's, like for most x's, there would be like some kind of small difference between these sets. So and for some x's, it's really bad. For a very small fraction, which is dangerous, it's really bad. Like maybe they have like, most of them is just one color, and the other is just one. So this is where this error comes from. The error, not from the dangerous, but for most things, it won't be exactly equal, but it will be like sort of equal. And this thing, this theorem can be generalized for gadgets with low discrepancy as well, easily using like Vasirani XOR lemma and things like that. So now we have uniform marginals, and we know how to not condition on like dangerous values. So this is our simulation algorithm from like top down. So we start at the root of the protocol, and at the root, we have not queried anything. So rows all stars, and we are thinking about the inner product gadgets. So x and y are both b and bit strings. And at the root, both x and y are one dense. Their min entropy is the maximum possible. So the density rate is not 0.9, it's exactly 1. So our invariants are maintained at the root. And now we need to sample the next bit. Okay? So, but we can by the invariance of our algorithm, we can assume that we are at a node where x cross y is row T structured. So with every node, we have some kind of row that the algorithm book keeps. And this node has this associated rectangle, which is tau structured. So basically x is dense and y is dense. And let's assume that Alice is speaking and Alice splits her inputs. So first, what we do is like we condition on x free not taking an epsilon dangerous value, because we don't want to go down that path. And this is not a problem because the probability of this happening is only like 1 over poly n. So with 1 minus 1 over poly n, we'll be like our simulation would not be deviating from the actual distribution that we want to sample. And now we sample the next bit with probability xd over x. Like if because of uniform marginals, we know that the marginal distribution of this TC, which is just xy sampled uniformly at random from G inverse of C, which we don't know what it is equal to uniform on X. So if we are trying to emulate that distribution, the good strategy is to sample the next bit based on the number of x's that go into x0 versus the number of x's that go into x1. So we sample xd with this density, this mass, and then we go down and go to that particular node. Okay. But by doing so, we might have lost density.
Wait, are we assuming here that x0 and x1 are disjoint?
Yes. Yes. So so far, everything that I've described is for tree-like protocols.
Yeah. No. But I guess, okay. Like suppose Alice is just wasting, I mean, she has internal randomness also, no? Or wait, are we thinking of the, are we in like a distributional setting where we fix the?
Yes. So what the decision tree algorithm does is that it samples using internal randomness, the randomness of the protocol pi. So it fixes pi with that randomness to get a deterministic protocol pi r. So this is all for a deterministic.
Yes. Yes. Yes.
Yeah. And if you are correctly sampling on a deterministic protocol, by expectation will also be sampling on the mixture of these distributions, right? So now, because we might have lost density on X free row, we'll do this density restoring partition, which is what we talked about in like a couple of slides. So again, the right way. So now we need to choose one of these partitions because we want, like, we know that X has lost density. We want to query some parts of X and restore density on the other parts. So to choose these parts, we use the same probability because we are going with uniform on X. Uniform X and X free would have gone into Xj with probability cardinality Xj over X free, right? Yeah. Basically, like this is X free, cardinality of X free is just cardinality of X because fixed parts are already fixed. So the way we did like this kind of density restoration, whenever we found some block I in X lacking in density, we fixed it to some heavy value. So now by doing so, we know that so we are in this part J and we entered Xj. In part Xj, we know that except for these blocks Ij, X free minus Ij is delta dense. Right? So what we do is we query Ij. We query Ij and we obtain Zj, and we update row of Ij to be Zj. We want to say that we have queried the coordinates Ij and we got the Zij. And then we want our y's to be consistent with the query answer. So we update y by the standard thing. Because we condition on X not dangerous, we know that by definition of X not being dangerous, we know that Y on the new free coordinates. So this was just the earlier free coordinates, union Ij. Sorry, not union, but set minus Ij. So minus Ij, it's delta minus epsilon. So by doing this set of the sequence of steps, we have ensured that we are in here, although we like focused on x0 cross I, our simulation has like branched into many parts, and we are in some part which is xj cross y dash, which is this y, and this xj cross y dash is now row tau structured. But it's not the same row, it's this updated row. So we have maintained the invariant. So here we are not like in the original rectangle inherited from Alice anymore, but in a part of that rectangle. Yeah, but end of the day, we have maintained the invariance. Okay, so now is the final part, which is the query complexity. Like, so yeah, so this ensures that we maintain the invariant all the time. And once you reach the leaf node, then an easy argument shows that whatever is the answer of the randomized protocol. That's some trickery on distributions of this distribution of deterministic protocols. I can do that like after we discuss query complexity. So now, assuming that like it's sort of correct, like we need to show that the query complexity is communication complexity divided by theta of b. Because of both index and inner product on b bits as communication theta of b, this is what we need to show. To show this, we use a potential argument. So at the and the potential is it's a measure called deficiency of xy. So what is the maximum min entropy of x and y? It's the maximum number of bits in the number of bits in the free coordinates of x and y. So there are b bits in the free coordinates of x, and there are b bits in the free coordinates of y. So in total, for inner product, this is this much. Okay, and then we subtract the actual min entropy of x free and actual min entropy of y free. So this is going to be our potential. So in particular, for the root of the protocol, this like h infinity of x free is the maximum, right? This is just 2b cardinality free. Sorry, not 2b, but just b cardinality free. And similarly, h infinity of y free is also 2b cardinality free. So at the root of the protocol, the deficiency of xy is just 0. And the way we have defined it, deficiency is always non-negative, right? The maximum value h infinity of x free can take is to like b times free, and similarly for hy free. And this can never be negative. This can be 0, which is at the root, but it can never be negative. So this is where like what Jakob was asking, like whether we are sampling like bit by bit, or whether we can sample the frontier of Alice. So suppose we have Alice, and assume that like Alice's messages are like a prefix code. So by looking at Bob knows whether it's his turn to speak. I mean, they're like separate. So if Alice, this are the messages sent by Alice. So this is M1, this is MK. They might be of the same length, they might be of different length, we don't know. So we, instead of choosing the next bit, you could like, okay, so if you're choosing the next bit, you would choose the next bit with the probability that you would have sampled that bit. So which is like the cardinality of xp by x, you would have sampled, but you could in fact just sample pm I with so you could sample mi with probability pmi. Right? So this increases the deficiency by logarithm of this probability. So for example, like if it is like if it's equally distributed, so if x, we are choosing the next bit, and x gets split into x equal halves x0 and x1, then this PB for both 0 and 1 would be like half. So this would increase the deficiency by 1. So if they're splitting information evenly, that's like they're sending 1 bit of information in every round, and then the deficiency would increase by that much. But in an arbitrary protocol, this could be like very different. But we know that at least one of them would be sort of around 1/2 to the maximum length, but that doesn't matter. So in general, it increases the deficiency by log 1/pp. Okay, and so on some messages, so especially in this round based communication protocols, like some messages could have like very small probability, even in the two-party thing. Like it could be that x splits x0 and x1, and x1 is like tiny, and x1 is, sorry, x0 is tiny and x1 is huge. In this case, the probability of sampling x0 is very small, right? So it would increase the deficiency by quite a lot. And on those branches, your query complexity would go up quite high. So we don't want to even like go down those branches. This is why I said like our decision tree can abort. So if the probability, let's say like cardinality of x0 over x is less than 1/poly n, again the same 1/poly n which we are adding to the error anyway, we'll just abort. We'll not even go to x0. We'll say that the probability that we would have gone into x0 is just 1/poly n, and we are adding that to the error. And because the error gets added over n steps, this poly n is like larger than, I don't know, n cube. This is still 1/poly n. So it's like in some cases our decision tree just gives up. Okay, so so by like going down the path, we are only like at any time we are on any path which doesn't abort, we are only increasing the deficiency by something like communication complexity of 5. Okay, so the deficiency increases by at most this much, or we abort. And every query, the deficiency decreases by ij times p. Okay, so this is omega ij times p. This is because we knew that like the density was we knew that the density was smaller than delta x. So at least 1 minus delta x times ijb bits have been communicated about it, right? So by conditioning away those coordinates ij, we're like not even, we don't care about the mean entropy on those coordinates anymore. We can, like an easy calculation shows that the deficiency decreases by ijp. Not exactly, but like something like 1 minus delta x times ij. But 1 minus delta x is a constant, something like 0.1 ijp. Yeah. So then this gives you that the query complexity is communication divided by omega p, because deficiency is non-negative, and the maximum number of queries that we do at any node is exactly the number of queries we do at a particular node is fixed row, even at the leaf node. And so fixed row is the number of queries. So fixed cc pi for minus fixed row times p, ignoring constants, is at least 0. So this tells you that number of queries is cc pi divided by some omega. So this shows us that our simulation is efficient. Yeah. And that is all I have on the slides. Yeah, if you're interested, we could I can go into some other details, but you know,
So I'm thinking that at some point we're getting to a stage where you need to sit down like carefully and do the calculations.
Yeah.
And I wonder
If
if
we
we
could do
might be
this.
might be reaching that stage. We're also 20 minutes over 4.
Oh, okay,
So,
sorry. This is
no, this is fine. I mean, this is great, but it might also be worth thinking about wrapping up.
Yeah, I mean, I can stop at this point. Like, this is where my slides, and then like I thought if I had time, I'd also talk about like the intuition behind finding these non-dangerous values. I could take like 5 more minutes to do that, like very high level. Not.
Let's do 5 high-level minutes.
Yes. Okay. Yeah. So just to show that the main technical lemma, which shows that like an X which is dangerous is highly unlikely. Okay. I need to start a new share. Yeah. Say this. Yeah. Yeah. So just some high level overview of like why we can hope to say that like the dangerous values are not too large. Okay, so we are looking at some y. We were looking at some y which is already delta dense, and we fix some xi to be alpha I. Okay, and we are worried about like what happens on conditioning we are conditioning on phi with gi of xi alpha I, sorry, not xi alpha I, xi is alpha I phi I equals zi. So after like fixing xi equal to alpha I, we also queried zi, right? So we so there are two things to consider. So one is like leaking. So leaking means that like you're revealing more than I bits of information, or rather the like the probability of this particular gi alpha I yi being ci is smaller than 2 to the I. So if there was no leaking, all the zi's would be equally likely, and you'd expect their probability to be like to show up would be around like by changing the yi would be around 1 over 2 to the I. But if it's leaking, it's more than that, right? So you're looking at so in leaking, you're interested in the min entropy of g to the I, alpha I, yi. So a particular value zi is like the min entropy is like what's the maximum probability of a particular ci. So we are exactly analyzing this, but we knew that y is delta dense. And because of the extractor property of our gadget, this would say that like for most x, but like x was like, so this alpha i's come from not a delta dense distribution x, but x had lost density. But in the case we were only sampling like a few bits, this density could not have gone down by much. or if we were like sampling the frontier, if the density goes down by too much, that means like we have communicated very few bits and destroyed the density by much like higher quantity. So in those cases, we would have aborted. Just because we didn't abort, it means that like this x from which we are fixing alpha I is already some delta x minus some 0.1 tens. So x is delta somewhat dense, y is somewhat dense. Uniform marginals would tell you that then if you sample from this for any z, xi, yi is like the marginals are the same, or in particular, like you show that like every zi is almost equally likely. Every zi that's consistent with the answer so far. So just by using that xi and yi are some delta x minus 0.1 tens and delta tens, we get that for most xi, this would be this would be at least I minus 1. At least I minus 1 is for some like, calculations. So it would have like the mean entropy approximately I. So this is the maximum mean entropy is anyway I, right? So this is like I bits in total. It's the gadget output on these blocks. So by just using this somewhat density, we can show that leaking is unlikely. So for most values, it would not be leaking. Again, so there will be some values which would be leaking, but that would come from the total variation distance and the uniform marginals. Potentially, I mean, they may not be. And now this is the easier one. Just follows from this. But what about sparsifying? This one is harder to handle. So here, what is sparsifying? Sorry, so sparsifying means that by conditioning on alpha I yi being some particular zi, we have lost density, delta y density is lost on n minus I. So in the unqueried coordinates, we do not have density. So even if we conditioned on x being not leaking, this could happen, right? Because in the case of index gadget, I can be much larger than the block size. And maybe like this is like so correlated that they all go into one block. But that means that there's like a lot of correlations between different blocks of y. But then that cannot be the case. Y is dense. Y originally was delta dense. So in the original Y, for most particular values, there cannot be too much of correlations because if you take any subset of blocks, they have high mean entropy. So one way to like analyze this condition is to look at it as effect of fixing some blocks of y on the gadget output. So what are we saying? Like we fixed gi of alpha I yi equals to some zi, and because of that we lost density on n minus I. So there's some j subset of n minus I, right? So that h infinity of this new y, let's call it y dash. Y dash is just y conditioned on this consistency requirement. So this h infinity of y dash was less than delta y b log m. Sorry, not log. So there's some set of blocks which lost their mean entropy. right? If alpha I was parsifying, this alpha I by zi is parsifying, just by definition. So now this another way to think about that would be this. Okay, so this by definition implies that there's some particular value yj, such that probability that this distribution yj is equal to this particular value yj conditioned on this event, it's less than, it's greater than, sorry, 2 to the minus delta y pj. It's strictly greater than this. Now, using a simple Bayes theorem application, you could now think of this as not as min entropy reduction on yj because the gadget output was fixed, but you could equivalently think of this as min entropy reduction on the gadget output because we fixed some particular yj. Okay. That's some small calculation. It's basically like it's saying that yeah, because of gadget output being fixed, this particular yj had a higher chance. So if you like, this in turn also implies that if you fix on this particular yj, then this gadget output is also going to be very highly likely. So what it said is that, okay, if this gadget output is this, then it's very highly correlated to yj being this particular yj. So in the reverse, it also says that if yj is yj, then the gadget, it's heavily correlated to gadget output being this particular zj, ci. So the reduction, like the yeah, so you can instead think of this as a reduction in min entropy of the gadget. So by fixing some yj, you reduce the min entropy of the gadget. But the min entropy of the gadget is quite high because we are in a non-leaking setting and we had uniform marginals because x was somewhat dense and y was dense. So we know that like for most x's and y's, this would not happen. So this correlation that like you can fix some unqueried blocks of yj and it could affect a particular gadget output. That's unlikely. So you can show that except for a few values x, most x are not specified. Does that make sense? So yeah, I think that's it. Yeah, a lot more things, but I think it's like not just. Yeah.
Okay.
Thank you.
Thanks again. So I think we also asked a fair number of questions during the talk. I'm trying to think about, is there any final comments or remarks?
Okay.
So yeah, I guess you already briefly addressed this. So this new sunflower technique that brings down the gadget size.
Yeah.
That somehow, but somehow the guarantees that you get from this don't obviously seem to be strong enough to work in a randomized setting.
No, so the proof of Lovett and Zhang, that doesn't give you the extractor property. So like, yeah, the parameter range that we're trying for, you don't get an extractor property for index using this new sunflower improvement.
Ah,
So it doesn't work in the randomized setting as it is.
I see.
This nice example where so they sample these kind of p-biased families of sets, and there are examples for p where the structure properties. So in the deterministic setting, I don't know, like so it uses this property of index to write down index xy as like a intersection of set systems. So it's not clear how to write in a product as like in that setting. Yeah.
Okay. Thank you again so much, Sajin, for this second in-depth part with a lot of technical meat to chew on. So thank you so very much.
Thank you for inviting me. This is great. Sorry, like I took way over time in the first part.
No, not at all. Thank you so much.